we have discussed what match filters can do for us, and we were now getting ready to discuss how they can help us in designing demodulators for various kinds of digital modulation schemes that we have considered in the past. And specifically we'll be discussing today, which we had started doing yesterday, coherent demodulation for binary waveforms. So today I'll basically take up binary waveforms of two kinds, namely the antipodal kind like binary phase shifting and the orthogonal kind like frequency shifting. Okay, so we'll take up these two, but before I get into this, I just want to point out to you that match filters have applications in many fields, not only in optimum demodulation in digital communication. They have applications in any kind of problem where you need to detect signals, right? What are the, can you name a few applications where you may need to do that other than communications, other than digital communications, where you need to detect signals, weak signals in noise, in the presence of noise? I'm sure you know of a few applications. Radars, for example, you transmit a narrow pulse and it gets reflected back, comes back very weak in the presence of a lot of noise and clutter, and the radar receiver has to decide at a particular range whether a pulse is present or not, right? So as to decide whether a target is present or not at a particular range. Again, another property of match filters can be used in such applications, namely the output of the match filter is the autocorrelation function of the waveform, right? Now obviously in such applications like radar and sonar, you would like the output pulse to be broad or narrow. The output pulse to be narrow. Why? So as to be able to resolve nearby targets, right? Because the resolution ultimately depends on how broad is the output pulse, right? So you can design a pulse shape there such that its autocorrelation function is very narrow, and thereby you can increase the resolution. You could of course get the same resolution by transmitting a narrow pulse, but the disadvantage of that is a narrow pulse with a peak power limitation will have a finite amount of energy, and therefore it will affect the detectability of the pulse, right? Because ultimately the output's SNR depends on the signal energy once the noise power is fixed. So it will be useful to transmit a wide pulse, but so designed that its autocorrelation function is narrow, right?
Why we can't have a narrow pulse in the first place?
Because if you have a narrow pulse and if you have a peak power limitation, which most of these applications will have, it will put a limit on how much energy you can put in each pulse, which will in turn affect the output signal to noise ratio of the match filter, right? And therefore affect your performance in terms of detectability, right? Therefore it will be useful to design pulses which are, let's say, broad to start with, which while transmitted are broad, but after match filtering they become narrow, right? So such waveforms which have such properties are called pulse compression waveforms. They are very useful in these are the kind of signals which are used for obtaining good resolution in applications like radars and sonars, right? There are other applications of match filtering also, even in digital communication, not only for demodulation but for other purposes. We'll perhaps have time to discuss some of these things later, but maybe we don't have time, so I'll just briefly mention some other applications of match filtering. If you may recollect, timing synchronization is going to be an important aspect of all digital communication systems, whereby we need to know precisely when the message, when a particular sequence of messages starts, right? Whenever you start transmitting, you don't want to lose anything, and therefore typically before you actually start transmission of a given message, you will be prefixing it with some kind of a preamble sequence, right? The purpose of transmission of this preamble sequence will be to designate very clearly the time instant from where onwards the message actually starts, right? So we will be transmitting some well defined a priori known bits to the receiver, and what the receiver will try to do is, based on this transmitted a priori preamble, it will match filter that so as to have a very narrow, sharp autocorrelation function output to pinpoint where the message actually starts. So it is useful in carrying out what is called frame synchronization. So match filtering is used also in frame synchronization. Similarly, match filtering has a lot of other applications in spread spectrum communication systems. However, we don't have time to discuss all of those things, but the main point that I wanted to mention before getting a bit deeper into the application of interest to us was that match filters have a very large class of applications, right? This is just one of these classes of applications. All right, you have any questions on that?
Will you just tell us what is spread spectrum? I mean, without going into details, if possible.
It will be quite digressive, so I think maybe in some other platform we'll do that, right? It will be quite digressive at this point. So let's first get to this business. So let's talk about coherent demodulation for binary waveforms. A few things we talked about yesterday, and one thing that we talked about was how to take care of the phase offset that may be present in the received signal, right, in the carrier of the received signal. All we have to do is to compensate for it by multiplying the complex envelope of the received signal by simply e to the power minus j theta. So after that, if our phase estimation is good, we can more or less assume, and this is what we shall assume for the present discussion, that we have no phase offset effectively, all right, because we have perfectly compensated for it. Of course, in real life we will never be able to do this estimation perfectly, right? Even your carrier recovery circuit will be affected by noise, so it will not be able to do a perfect estimation of the actual phase. So there will be some phase jitter which is still left over and will affect the performance of your system. But at the moment, for the discussion of looking at the demodulators for these waveforms, we will assume that we have perfect phase compensation possible, and we will therefore ignore it.
So how can you have an estimate of the theta? Isn't it quite random? How do you say that theta is known?
Yeah, theta is going to be known to us provided we do something at the receiver, and that something is carrier recovery circuit, right? That is a circuit which is specially designed to track the carrier frequency and phase. So we are assuming that such a circuit is in operation at the receiver, and from its output we have an estimate of theta available, which we shall use to compensate for the value of theta that has taken place, phase shift that has taken place. So this is precisely why I am saying that since this estimation is not going to be perfect in practice we will not be able to compensate for it perfectly, and therefore this assumption of a zero phase offset will not be strictly valid in practice. However, we shall assume that it is valid for the present treatment. Okay, so to start with, let me discuss this picture for the demodulation for antipodal signals. So I am taking the case of antipodal signals here, of which BPSK is an example. Binary phase shifting is the main example of antipodal signaling in most practical applications. Although there could be, in general, antipodal signals can be defined in terms of any arbitrary waveform ST, right? So recollect that we can represent a general binary signal which uses the pulse shape ST as a sequence of such pulses, right? L going from minus infinity to plus infinity. A sub L's are your bits, right? Taking the values plus minus 1 in the case of antipodal signaling, right? And this is your basic pulse shape, which could be of finite duration or it could be of infinite duration, depending on whether it's let's say rectangular pulse or a Nyquist pulse, right? It could be anything. This sequence of positive and negative pulses gets corrupted by noise, and that's what you receive at the receiver in the form of the signal Vt. Alright, and the receiver or demodulator for this kind of digital modulation scheme is obviously very trivial now after our discussion of match filtering. What we do is pass it through this sequence of pulses coming one after another is actually demodulated one bit at a time. Suppose this is a bit interval, right? We transmit, we demodulate it one bit at a time. So every incoming pulse excites this match filter, produces an output which is expected to peak where? At t is equal to 0. No. Now this is where you have to be careful. Of course, I have shown here at t is equal to 0, but it's actually going to peak at. I should really put here s t minus t, because we want it to peak after the pulse duration, right? After every pulse duration we want it to peak, right? But symbolically I'll typically write it as s of minus t, right? So typically at the end of every bit interval, this is supposed, the output of the match filter is supposed to peak, and that is where I will sample the output of the match filter, and if it was a positive pulse, I will expect this peak output to be positive. If it is a negative pulse, pulse shape is same whether it is positive or negative, so it will keep on producing the autocorrelation function, the peak value of the autocorrelation function, the output, except for the polarity of it, right? Polarity will depend on whether A sub L is positive or it is negative. So if I get a positive large peak, that implies, let's say, a 0 or a 1 was transmitted. Either way it's a matter of how you map the signal, and if it is other way around, it's the other bit, right?
What did you say about S of capital T minus small t?
That was to do with where the peak will occur, right? Suppose I am considering the very first bit interval 0 to t, right? If I want the peak to occur at t equal to capital T, the impulse response to the match filter should be S capital T minus t. Your t sub 0 is capital T, right? And so on for every bit interval. So really speaking, I would like it to be peaking every t seconds, and I would like to keep on sampling the output of the match filter every t seconds, right? Is it okay? However, you must note that the fact that it is peaking at t equal to LT for every t seconds, every t second interval, does not imply that the match filter output is 0 elsewhere for a particular excitation interval, right? It may not be 0 elsewhere. In fact, even if your pulse is of finite duration, the minimum duration of the match filter output will be, suppose this is strictly of duration t, in each incoming pulse is strictly of duration t. What is the minimum width for the match filter output? 2t, because the impulse response is of duration t, the input pulse is of duration t, the convolution will be of duration, which is the sum of these two durations, which will be 2t, right? So although it is peaking at t equal to capital T and therefore then capital 2t and so on, we do have the distinct possibility of intersymbol interference here, right? Because the output of the match filter response, the match filter response does not become 0 in the next bit interval, it remains finite, and so on for subsequent bit intervals, right? So what we have to make sure is that this pulse shape indeed, not at the input but the output, satisfies the Nyquist criterion, right? That is, pulse shape that we choose be such that at the sampling instance the Nyquist criterion is satisfied. That is, when the output of the match filter is peaking due to the current pulse, the response of the same match filter to all previous pulses is 0 at that time instant, right? We don't care what the response is at other time instants. but at multiples of t seconds the response becomes 0. This is something we are familiar with. We will discuss that separately at length when discussing the transmission of pulses in band limited channels. Alright, so we are familiar with that fact. Therefore, the net result is, if the Nyquist criterion is satisfied, the net result is that the output can be detected now. Of course, there will be variation around this peak due to the presence of noise. We will not get the true peak value which you would have expected if signal alone was the input to the match filter, right. If signal alone was the input to the match filter, there would be no problem, right. But since the signal is associated with noise, this peak values will be associated with some variability due to noise, with some variance, and therefore there is a need to put a threshold detector there, and all we can say is, if the peak is positive, take one decision; if the peak is negative, take the other decision, right. This makes sense.
So what is that decision?
This sampled value is called the decision statistic, on the basis of which you take a decision. Okay, this is a terminology I picked up from detection theory. In detection, decision statistic, it's written there. Okay, this is the sample values that are coming over here every t seconds are called the decision statistics, because it is on the basis of this sample value that you decide whether a 0 or 1 was transmitted, right. So this term has come from there. So broadly the scheme for antipodal demodulation is clear. Okay, so just briefly let me mention this fact that I just discussed with you, that the signal pulses at the output of the match filter must not exhibit intersymbol interference, right. The signal should be so designed in this scheme of things that the pulses at the output of the match filter, although exhibiting a peak every t seconds, should also contribute no intersymbol interference, right. So signal pulses at the output, at the match filter output, in other words, there should be Nyquist pulses, right. Okay, which essentially means that we must choose for our antipodal signaling a waveform or a pulse shape ST such that the match filter output due to the signal, which remember I had denoted by RT, right, which would be essentially the convolution between ST and S conjugate minus T, right. This should be equal to one of the Nyquist pulse shapes that we have discussed. For example, it could be a raised cosine shape, the time waveform corresponding to the raised cosine pulse, assuming the channel to be ideal. In fact, that is how we have modeled the channel for this discussion, right. All I am saying is that the channel does not distort the signal, right. If the channel distorts the signal also, then correspondingly a match filter, your receiver structure has to change then, and that is a situation that I am not discussing at the moment. I have idealized the discussion a bit. I am assuming that channel is ideal, and therefore the waveform does not change, and channel itself does not introduce intersymbol interference, right. So the intersymbol interference that we have taken care of is the one which could have been introduced by the transmitter filter and the receiver filter, right. And therefore if there is such a distortion, we have to take care of it separately. Our receiver becomes more complex, right. If we have time, I will discuss that issue separately. Okay, so now you have some idea about what one does with that raised cosine pulse that we designed earlier, right. At that stage we had just left it there, that when we discussed transmission of pulses in band limited channels, we just said that our overall pulse shape should be such that it exhibits no intersymbol interference, and from Nyquist considerations, we said that such pulses could possibly be of these kinds of shapes, right? But now we know something more than what we did at that time. We now know how to split that pulse shape into the transmitted pulse shape and the receiver, into the transmitter pulse shaping filter impulse response and the receiver impulse response, right? That splitting should be such that the convolution of these two should be equal to that pulse shape, right? At that stage we did not discuss this issue, but now we know something more, that somehow these two things have to be put together.
So we put another constraint on HT, using HT.
No, at that stage we did not in fact choose HT.
I mean ST.
Yeah, we only discussed what was the final shape, pulse shape we wanted. Now we can say what is the actual transmitted pulse shape that we should use, right, at the transmitter. It is linked with its match filtering later at the receiver, right? The convolution of the actual pulse shape that you use and the match filter impulse response should be equal to the Nyquist pulse. It need not be raised cosine. Any Nyquist pulse shape will do. Okay, raised cosine is just an example. Any point to discuss or any doubt here? Okay. Now I have discussed one basic realization for antipodal signaling, which is essentially that each incoming pulse is match filtered and its polarity detected at the sampling instant. That's what the demodulator turns out to be. In fact, it can be shown to be optimal from the probability of error point of view in Gaussian noise. I am not going to do that, but it's very simple to do that. In fact, when we look at the performance of this receiver, it will become obvious that it is optimal. Now there are other possible implementations of this receiver, particularly when the pulse shapes that we use, let's say, are passband pulses, right? That is, they are embedded onto a carrier. Right now I chose a general pulse shape. I didn't discuss whether it was a baseband pulse or a passband pulse. It could have been anything, right? The result would have been the same. So the need to discuss that issue separately is important, because when we are discussing passband pulses, a lot of other issues crop up, and I like to at least pinpoint some of those issues. The basic structure does not change. The basic processing that we need to do remains the same whether this is a baseband pulse or a passband pulse, right? Basic operation has to be the same, match filtering followed by polarity detection after sampling, right? But some of the other issues crop up which are important, and therefore I like to spend a little bit time on alternative realizations, particularly in the case of passband. For example, if you really talk about binary phase shift keying, the presence of a carrier is implied, right? Therefore we are talking about a passband signal. Okay, one could have the same match filter implementation like I have got over here. Your received signal is coming in, the match filter, because you I'm again assuming carrier offset to be 0, phase offset to be 0, so that if you transmit a signal st cosine 2 pi f naught t, now this is your baseband pulse shape which is embedded onto the carrier, right? And this will come along with positive or negative amplitude. That is what binary phase shift keying is, either cosine 2 pi ft or minus cosine 2 pi f naught t, right? So depending on whether a sub l is plus 1 or minus 1. This is what you are receiving. The corresponding match filter will be a filter with impulse response s minus t cosine 2 pi f sub o t. All right.
So the previous case was general, it was not BPSK.
It was general antipodal signal, right? BPSK is a special situation where the pulse is embedded onto a carrier, right? That is when we can talk about phase shift only when you have a carrier, right? Isn't it? Without a carrier it is meaningless to talk about phase shift. We just say it is antipodal, right? BPSK is an example of antipodal signaling, and that obviously implies the presence of a carrier.
The output of this match filter, passband match filter, is another passband output.
Yes, it is a passband pulse.
So it will be fast varying output, and if we sample it at some instant, it will go to.
But we know that even that passband pulse is supposed to peak at t equal to capital T, right? We have seen that yesterday. Remember that?
It will peak, but value may be negative. We are using polarity detector.
Yes.
So
let me see if I can get hold of that picture which I presented to you yesterday.
तो ये बहुत फास्ट होगा, बहुत कम टाइम के दिखा है. तो सैंपलिंग से आप करेंगे.
So, but we are using polarity detector.
Just let me give me a second, please. We discussed that yesterday, right? This is a passband pulse. After match filtering, this is how it will become, and you are going to sample it here, right? If it is now, if the polarities change, the phase is changed by 180 degrees, what will happen? The whole thing will come upside down, and this peak will be seen here.
So because it is very fast varying output, so
That is a separate problem, and that is a problem I really wanted to discuss. That's good. You could think of that. Yes, because this is because of this fast variation in the pulse carrier at the output, it's going to be sensitive to timing error.
at baseband it won't be such a problem, but at this
Right.
it will be.
You got it. Very good. That's the point I was coming to. So the base straightforward implementation is obvious. Just replace that match filter with the corresponding match filter here, and the problem, as rightly pointed out by Varun, is that this kind of arrangement is going to be a bit sensitive, in fact quite sensitive to timing errors. Let's see that in some detail. The pictorially it is quite obvious, right, from the picture that I have drawn it, but let's do some analysis and try to appreciate to what extent there will be problem. The output of the match filter corresponding to this situation can be written like this. A sub L This is quite obvious, so I am not going to explain this any further unless you would like me to. Okay. This is the signal part of the match filter output, which essentially consists of the baseband output pulse modulating the carrier, right? And that's the noise part, where NR prime and NI prime are the convolved outputs corresponding to noise. What really is of interest to us is the sample value of this output waveform at t equal to LT at the sampling instance, right? What will be this output at t equal to LT? If cosine 2 pi f, if we design cosine 2 pi f naught LT to be 1, right, and if we make sure that these output pulses satisfy the Nyquist criterion, then the only contribution that will come at t equal to LT will be from A sub L, right, because all other bit values will not contribute to the value as sample at t equal to LT, alright. So it will be A sub L. We are also assuming that at t equal to LT, cosine 2 pi f naught LT is equal to 1, right. Similarly, this will become NR prime, some value LT, and this will be obviously 0 then, because if cosine is 1, sine will be 0 at that point, right. And that tells you the sensitivity. For example, if you sample it at somewhere else, for example, if you sample at t is equal to 1 by 4 f naught plus LT, what is going to happen? What is going to happen to this cosine? It is going to become sine, right, pi by 2 phase shift. So your signal will disappear altogether,
And 1 by 4 f naught is small time.
right? And if f naught happens to be high, if your carrier frequency happens to be high, that's a very small timing offset. Okay, So this just mathematically demonstrates the same issue that we saw pictorially. So what is the solution? There are two possible solutions. One is to use a carrier frequency which is small enough. Of course, that is not going to be under our control. That will really depend on the communication system in which we are with which we are working. If it's a microwave system, it has to have a microwave carrier frequency, right? If it's a voice band channel, then of course f0 will be relatively lower, but the corresponding data rates are also smaller, right? So in any case, the timing error problem can be solved by relatively changing the value of S sub naught, and one way to do that is known to you. What is that? Use an intermediate frequency receiver, right? That is, don't do the demodulation, passband demodulation straight away. First bring it down to a lower carrier frequency so that the sensitivity to timing error reduces to some extent, right? Of course, you are not exactly solving the problem, you are just passing on the problem somewhere else. Can you appreciate that? So this is an alternative passband BPSK demodulator, which is the same as before, except that instead of the match filter being matched to S minus t cosine 2 pi f1t f4t, it is matched to some other frequency f1t, which is an intermediate frequency of operation. So obviously it's implied that you are first translating the incoming signal down to this frequency by beating it with a local oscillator frequency of f0 minus f1, okay, and everything else is same.
Why don't we bring it right to the basement?
And alternative is to bring it right down to baseband. There are pros and cons. Sometimes this is easier, sometimes that is easier. Now, just to make sure you appreciate this fact, I would like to again reiterate that you have not solved the problem of timing sensitivity. All you have done is you have shifted it to now this place here, right? Suppose there is a carrier offset here with the local oscillator, that will again manifest itself in the form of a timing offset there, right? Therefore, all you have done is, okay, the timing circuit, you see, we have in any digital communication system, there are now, you appreciate, two kinds of synchronization you have to do. One is the timing synchronization. You should know where a new pulse is starting and ending, right? That is the timing sensitivity aspect. The other aspect is a phase synchronization, right? We have discussed now both of these briefly. I mean, what they are about. How they are done, we have not discussed, but what they are about, we have discussed. So we still have the problem of phase estimation, and basically we are shifting the timing sensitivity problem to phase sensitivity problem. Fortunately, the phase tracking circuits are easier to design as compared with timing synchronization circuits, right? So it's worthwhile shifting this problem from timing to phase tracking, from time tracking to phase tracking, and use of intermediate frequency helps us to do that precisely. Any questions? Vic? Fine. Now we have discussed therefore three different implementations for demodulation of antibodal signals, one general and two for the case of BPSK. I will also like to discuss one more implementation which is sometimes used, and that is correlator implementation. Okay. Before you draw the picture, let me just briefly discuss the idea behind it. I think you already know the idea behind it. Do you recollect? I discussed this in the context of match filtering.
Match filter is same as correlator.
It is not the same. Match filtering operation is not the same as correlator operation. However, if you confine your attention to the output at t equal to capital T or t equal to 0, whatever your output sampling instant is designed to be, right, then we can regard the two to be equivalent, right? The output waveforms are not the same, but the waveform value at the sampling instant of interest can be made the same. because suppose our designated sampling instant is t equal to 0, then we have appreciated before, we tried to discuss that several times, that this value r of 0 is nothing but the correlation of the received signal with the transmitted signal, right. So we can as well replace match filtering operation by correlation operation. The advantage of doing that is, suppose your pulse duration, the pulse is strictly of a time limited nature, right. This correlated implementation becomes very easy. See, the match filters that I have talked about in the BPSK case, for example, the so called passband match filters, they are essentially tuned filters, isn't it? When I say a filter with this impulse response, it's essentially a tuned filter, right, with a certain kind of transfer function which is dictated by this shape, because the Fourier transform of this is going to be the actual transfer function, right. Whereas in a correlator I don't implement any filter at all. All I do is take the incoming signal, multiply it with this, a local replica of the expected signal, and integrate. And integration is a very simple operation to implement. So implementation wise it is very convenient.
So
right?
but we have to reset the integrated.
That's right. We have to restart the integration every bit interval if we want to share the same integrator from one time interval to the next. Of course we could have a number of integrators for different time intervals, that will not be very convenient, right. So what we will do is have an arrangement like this. This is your incoming signal multiplied by the replica of local replica of the expected signal pulse shape what you transmitted. If it was a passband pulse, it will be st cosine 2 pi f naught t, and then integrate the result. And the result of integration at t equal to lt every t seconds is what you are interested in. And if you want to share the same integrator over and over again, you must reinitialize this integrator every t seconds. That's why we call this integrate and dump operation. That is, integrate for t seconds. Suppose I have a rectangular pulse, what will happen? Let's just try to appreciate the effect from a rectangular pulse. Yeah, suppose your transmitted pulse was a rectangular pulse. I will even forget about the carrier for the moment. So your local replica is also rectangular, right? You will multiply the two and integrate. Product will be a rectangular pulse again, and on integration you will build up the integration like that, right, from 0 to t. You want to sample this pulse. If one was positive and the other was negative, for example, if your transmitted pulse was really negative and this replica is of course the same, then it will build up like that, right. So in any case I need to sample this value, and then I must be ready for the next integration, and therefore I must reinitialize the integrator back to 0 after sampling it, right. That's called a dumping operation, so that you are ready for the next. Maybe this was a positive pulse, this was a negative pulse, so you dump it again, and the next one also could be negative pulse, and so on. So you keep on sampling these, then dumping the integrator output to, that is reinitializing the integrator and carrying on the operation, and the rest is all the same. So this is yet another possible implementation for BPSK demodulation. However, note that this kind of thing will be almost impossible to do if your pulse shape is not strictly time limited. You appreciate that? Right? For example, the Nyquist pulses that we have been talking about, if we are using those Nyquist pulses, then integrate and dump is ruled out. That is, we can't share the same integrator or successive time intervals, right. So you must appreciate that fact. Any questions? Can we go on to the next? I think that more or less covers binary phase shift keying demodulation or antipodal digital demodulation, right. Let's now come to demodulation of any issue that you would like to discuss. The other kind of binary waveforms you can have, namely orthogonal waveforms. Okay. Of which the most important example is binary frequency shift keying, right. But first I'll do a general discussion irrespective of whether it is frequency shift keying or something else. I mean, as long as the waveforms are orthogonal, they are orthogonal. And if you remember, binary FSK is a kind of general nomenclature for this class of waveforms, even though your orthogonal signaling scheme may not involve a frequency shift, right. It may be some other kinds of orthogonal waveforms, right. So therefore first I'll do a general discussion and then we'll mostly concentrate on FSK. Alright. I hope you remember the discussion of orthogonal waveforms. Well, you had a minor recently, so you must be remembering something. Before I go on to telling you what the demodulator should be like in this case, can you make a guess? Can you hazard a guess?
Bank of correlators.
A bank of correlators. Well, in this case we are talking of binary. We have to have only two, right. Well, let's first talk in terms of match filters, right. We need two match filters, one match to each other two waveforms. We discussed that yesterday also in the context, in a slightly different context, but now we are doing it in the context of demodulation, and this is what your demodulator will look like for orthogonal signals. The received signal is processed by two match filters now simultaneously, right. Obviously one of them is matched to it, right, depending on which one was transmitted, because your transmitted waveform is one of these two. You don't know which one a priori. The whole idea of the demodulator in this case is to find out which of these two waveforms was transmitted, because that tells me whether a 1 or a 0 was transmitted, right, for the binary case. And therefore what I need to do is I expect the match filter output, the right match filter output, to be larger than the other match filter output, isn't it? Because in one case, you remember we showed that yesterday in our match filter properties, if you have these orthogonal filters, it will produce an amplitude A in one and 0 in the other, right. Of course there will be noise in both, but since the mean of one is supposed to be larger than the mean of the other by a considerable amount, in general we will expect the correct match filter to produce the larger output, and therefore we just subtract the two. Depending on the polarity of this, we again decide whether this or that was a correct transmission, and therefore whether 1 or 0 was transmitted. That's the intuitive picture. Is it okay? Some maths. We will take the case where your received waveform is Vt, which is signal plus noise, right. So let's see what kind of conclusions we can draw mathematically. This is the physical picture, but let's just write down a bit of math so that we can do the analysis later when it needs to be done. The received signal can be written as a sequence of orthogonal pulses like this. Alright, you are either transmitting S0 or S1, right. Now AL prime is taking only the logical values 0 and 1. In this case we are not allowing these ALs to take positive and negative values, but only the logical values of 0 and 1. So either we are transmitting S0 For example, if AL prime is 1, we are transmitting S0. If AL prime is 0, we are transmitting S1. That is how one can represent this, plus the noise that is coming along, right, plus my NT. So your output of the match filter, output of the, let's say the first filter, suppose this is passed through, we are passing this waveform to both of these, right. So let's look at the output of the first filter, that is a top filter here. That will be given by U naught T AL prime S sub O. I can replace this with R, right? T minus L prime T. And what will this be? Well, we'll leave it like this for a moment. AL prime S1 T minus L prime T convolve with, we are convolving with SO, right, plus NT convolve with the same thing. Let me call that N prime. There is no place to write it here, so I will write it on the next page. Is that fine? This R naught represents the convolution of S naught with S naught, right. This is a convolution of S1 with S naught, and plus we will have NT convolve with S naught. I will call that N prime, and N sub O prime, because this convolve with S sub O. So plus N sub O prime T. Okay. In particular, if you sample this output at t equal to LT, what will be the output? This, let's try, just have to appreciate this. What will be this value, this convolution? If S1 and S0 are chosen to be orthogonal, this will be 0, right. So really it will be getting contribution only from this, right. So U naught LT is simply AL plus, because all other values of L prime, will not contribute if again we have chosen the pulse shape carefully so as not to exhibit intersymbol interference, right. So out of this summation, only the Lth value will be of interest, or will be what is going to be shown out at the output. So this will be this plus N, I will just call it NOL prime, which is a sample value of this. Similarly, the output of the lower filter, the other filter, the same thing is being processed by both the filters, right. The output of this other match filter, which is S1 minus T, you can appreciate will be, let's call it U sub 1, is going to be, it will be now AL bar plus, let's call this N1 L prime, alright, same argument, nothing changes. And now your decision is going to be based on sampling both of these and deciding which one is larger, right. This is one way of taking the decision, or you could subtract one from the other, which is what we are showing, which is what we are shown in that picture, right, so as to use a threshold detector. So your decision statistic could be either choosing the larger of the two values and then deciding which is larger, or alternatively, let's say subtract U1 LT and U0 LT, depending on whether this is greater or this is greater, we decide, I mean whether the result is positive or negative, we may decide that we transmitted a 1 or we transmitted a 0.
So here the dependence on the noise magnitude amplitude is too much. Like what we are deciding on is the signal part plus the noise part.
It's always going to be there.
But
What the match filter will do is it will try to minimize the amount of this noise.
So the difference of the two is that
Right.
would calculate everything.
No, the two noises will be uncorrelated. Remember that. So they will not cancel.
It will be
The variance will in fact become double. Right? When you add or subtract two uncorrelated or independent noise components, the variance will be doubled. Right? So subtraction is not going to help at all in that process. The only way the noise is being taken care of is through the fact that you are doing match filtering, and therefore these values will be as small as possible, right? And this is the best one can do, right? There's nothing better one can do about it. So that's a good point, but yes, one has to live with this noise. And obviously your remark is correct in the sense that it is well known that a binary orthogonal signaling scheme in general will have a poorer performance as compared with the corresponding antipodal scheme, right? And this is linked with what you are saying, okay, because of the fact that noise will be making it more sensitive. So this is the maths behind the same structure that we discussed. Okay, now this discussion is for a general yeah, I'll stop in a minute. This discussion is for a general orthogonal signaling scheme. We'll try to look at some special aspects of it in the context of FSK, particularly because when you're talking about FSK, we're talking of a carrier again, right? And what kind of issues come up and how we can simplify the implementations, etc. One general question I have is, let's say Varun remarked at one point that I could have a baseband implementation of the BPSK receiver, right? Can you tell me how could you have a baseband implementation?
In this model, just F1 is replaced by F0.
F1 is
you can just
Beat it with F1 and then you have baseband demodulation. Now when you do a general, one can also do it for a general situation, and I'll discuss that next time in the context of orthogonal signaling, where it is not necessarily BPSK, but for any arbitrary passband signal that you may have, you can do the demodulation at baseband, and the way to do it would be to first represent the passband signal by its complex envelope, right? So an important question is, how do you derive the complex envelope from the passband signal? We have discussed that before by just doing two of these demodulations, namely one with the cosine carrier and one with the sine carrier. So that gives us the complex envelope, complex representation. After that we can work in the complex baseband domain. Everything is baseband after that, right? So, and we'll use that for doing demodulation of FSK at baseband as well as at passband. Thank you very much.